Okay, so let's find the extreme values of fxy equals x squared plus 2y squared on the circle x squared plus y squared equals 1. Okay, so this is our constraint here. That's our g of x, y equals k function. Okay, so if we use the method of LaGrange multipliers, what does the LaGrange multiplier say? Well, it says for this extreme to occur, we need that the gradient of f equals some lambda times the gradient of g. Okay? So, our gradient of f, that's just the partial of f with respect to x, partial of f with respect to y. So that would be 2x and 4y, right? Partial with respect to x would be 2x plus 0. There's no x in the second one. Partial with respect to y, just be 4y right there. Then our gradient of g, what's our gradient of g? Well, that would just be the partial with respect to x, comma the partial with respect to y, that vector. 2x would be the partial with respect to x, and then 2y would be our partial with respect to y. Okay, so we want the gradient of f equal to some lambda times the gradient of g. And so here's what we've got. We've got lambda times all these. And so for these to equal, what have we got? 2x equals lambda times 2x? Yeah, because we've got to factor that in. Really? Yeah. Then 4y equals lambda times 2y. Now, notice that's two equations, but I have three unknowns. But I do have a third equation, because that's our g of xy equals k. So that's our third equation, if you will, for this. Okay. All right. Now, these, they come in all shapes and sizes. Some, it's not a one-size-fit-all solving technique here that works. On this one, what I can do is actually, if I set this to 0, then I can use a little factoring here and get some solutions going, can I? Factor off of 2x, and so I have 1 minus lambda equals 0. And so that means either 2x equals 0 or 1 minus lambda equals 0. So this would mean x equals 0, lambda would be 1, okay? Now, if x equals 0, what does that mean in terms of y? Well, here we have x and y related together, and so if x equals 0, then I've got 0 squared plus y squared equals 1. What have I got? Y squared equals 1, so y would either be plus or minus 1, right? Now, so that gives us two values there to check. So remember those. But we've also got this lambda equals 1, and so let's see where that takes us. Just got to explore all our options here. If lambda equals 1, then from this equation, we've got 4y equals 1 times 2y. Which that's going to give us another different solution there, isn't it? Because that would be 4y equals 2y, which is 4y minus 2y equals 0, which is y equals 0. That's different than anything I've got so far. So let's plug that into our x squared y plus y squared equals 1. So we get x squared equals 1, so x is plus or minus 1. So we get, not terribly interesting points, but we also get 0 plus or minus 1. So how do we, that's where our extreme values are going to occur, or could occur. So how do we figure out what's the max, what's the min? Just plug them in, right? Just plug those in. So let's do our, f of, I don't think it'll matter if f is 0 plus or minus 1 because of the way f is made here. You plug in a 1 or negative 1 for y, you get the same thing, right? 0 plus 2. It'd just be 2, wouldn't it? Then if we plug in this one, wait, what did I do? Oh, I did. Here's what I did. This one's different because this one's plus or minus 1, 0, isn't it? So we got plus or minus 1, 0. So it'd be plus or minus 1 squared plus 2 times 0 squared. So that would be 1 plus 0. So that would be 1. Yeah, so the maximum is going to be 2. The minimum is going to be 1. It doesn't have a very wide range, does it? Based on this constraint, anyway. So the max is f 0 plus or minus 1 equals 2. Run out of room here. And the min is f of plus or minus 1, 0 equals 1. Those are extreme values based on this constraint. If we change the constraint, that's going to change our values, because if we said x squared plus y squared, for example, equals 2, then that's going to change how our x and y are related. Probably wouldn't be that hard to figure out. I think it would just be whatever your square root of that is. That'll be whatever. So anyway. Okay. All right. So it's a little different from our previous. The previous method we would have done is, well, probably changed up, solve for either y or x there and plug it in, get it to a one variable equation. That's how we would previously done it. Whether or not this is easier probably depends on the function. Okay. Yeah. Okay. just a different way of going about it. All right. So let me redo a problem we've done earlier, and just to show you that this method does give you, because on this one we know what our extreme values are. We've previously done this problem, so we can show that this method does work, for one thing, and another type of system you can run into. Okay. All right. So let's go back to this one. Find the dimensions of the box with no lid that has minimum surface area if the volume is 200 meters cubed. Okay, we did that one previously. And we know that if this is our dimensions, x, y, and then this is z, we saw that the minimum is when x and y are the same, cube root of 400, and then the z is half of that. That's our minimum surface area. Well, let's see. Let's use LaGrange multipliers to do the LaGrange multiplier method. We do get that very same thing. Okay. All right. So LaGrange multiplier method. Well, first of all, we've got our surface area. Just have the one xy surface because we don't have the top. And we've got two xz's and two yz's. And then we have the volume is xyz, but we know that's our 200. Okay? So this is our f of xyz equation, and this is our g of xyz equals some constant equation, isn't it? Okay? So what do we know? To find the minimum here, we know the minimum is where the gradient of this equals lambda times the gradient of g. So what does that give us? Okay, this would be just the partial with respect to x, right? Y plus 2z. The partial with respect to y, x plus 2z, because that would be 0, no y in that. And then partial with respect to z, because it's an xyz, that would be 0, so that would be 2x plus 2z. 2y, sorry. Thank you. Equals then lambda times our gradient of g. So this is g right here. Well, we just need the partial with respect to x. So yz. Partial with respect to y, xz. Partial with respect to z, xy. Okay. So that gives us three equations, doesn't it? We'll have y plus 2z equals lambda yz. Then we'd have x plus 2z equals lambda xz. And then we'd have 2x plus 2y, lambda xy. That's how parallel vectors work. All right, but that's 4 variables, 3 equations. What's our fourth equation? This one right here, right? X, y, z equals 200. Okay, so that's 4 different equations. Different ways. Here's the way I see to do it. If we solve all these for lambda, we'd have y plus 2z over yz equals lambda. X plus 2z over xz equals lambda. And then 2x plus 2y over xy equals lambda. All those are equal to lambda, so they must be equal to themselves, right? Equal to one another. Okay, so we have y plus 2z over yz equals x plus 2z over xz equals 2x plus 2y over xy. As they say, solving these systems sometimes takes a little ingenuity. Okay. Now, what I can do to kind of help myself out here is all these bottom things are different. If I make them the same, then I've got something. So I can make these all be the same thing if I make them all be, say, x, y, z. Yes, so multiply this one by x on top. So that's x over x, so that doesn't change anything. This one needs a y, so we'll multiply top and bottom by y. And then multiply this one by z. Okay. So now essentially all the bases here are the same. So they kind of cancel. Yeah, so we have xy plus 2xz equals, it's right here. Let me erase, I think we're done with all that. So we have xy plus 2xz equals, so these are all gone, xy plus 2yz equals 2xz plus 2yz. Okay. And we also have the xyz equals 200, which eventually we'll get to. We'll use that. We haven't used that one yet. All right. So what are we going to do here? Well, I notice about the first two that I have something in common. They both have an xy in them. So I have xy plus 2z equals xy plus yz. What must that mean? 2xz better equal 2yz? Okay. So if that's to be true, then yeah, 2x must equal 2y. Cancel the y. Cancel the z. Aha. X equals y, which we knew, right? We just don't have the... We knew starting out that's what we should get. All right, but that doesn't give us a value for it. So, but it does give us something to work with. Now, if we take that and then say plug that into two of the others. Yeah, let's do the last two here, okay? So if I plug in the fact that x equals y equals x, if I plug in x for y, right, because I can make this substitution, y equals x. So let's plug in y to be x. So I've got xy plus 2yz. Just go ahead and write it. 2xz plus 2yz. If I make the substitution y equals x, x squared plus 2xz equals 2xz plus 2xz. Okay. Yeah, subtract 2xz, so we get rid of that. So x squared equals 2xz. Let's do this. Let's just solve that little equation right there. X equals 0, but is that any good? X equals 0? If x equals 0, that makes my volume 0. That won't work. So x minus 2z equals 0. What does that tell me? x equals 2z, so z equals x over 2. Which we knew that was also our minimum value, half of x. But that still doesn't give us the number for x. So that's where this one comes in. Now that we know x equals y, or y equals x, and z equals x over 2, can't we use this? So x, y, z equals 200. But now we know y equals x, so we can substitute x there. Z equals x over 2, so we can substitute there. So we have x times x over 2 equals 200. Multiply by 2. So we have x cubed over 2 equals 200. So x cubed equals 400. X equals cube root of 400. So y equals the cube root of 400. Z equals cube root of 400 over 2. All right? Ta-da. Same thing. Same thing. Same thing we found previously.